I want you to picture a scenario that has, well, almost certainly happened to you this week. You get a calendar invite for a meeting. You tap the Zoom link on your phone.
No, yeah, classic.
Right. Your phone opens your web browser. The browser loads this blank white page for a split second, then pops up a prompt asking, open in Zoom.
Yeah.
You tap yes, but instead of actually launching the app, the browser just reloads that same blank page. Or, maybe it dumps you into the App Store,
Yeah.
and you are just caught in this infinite maddening loop, tapping the exact same piece of blue underlined text over and over, just hoping the operating system magically figures out what it's supposed to do. But then, like 10 minutes later, someone texts you a Slack link, you tap it, and you are flawlessly, instantly teleported right into a specific chat channel without a single glitch.
It is a totally fragmented user experience. I mean, we mentally categorize all of these things under the single umbrella term of links, right?
Yeah.
But under the hood, your device is wrestling with drastically different computing mechanics. The routing logic happening beneath the glass is incredibly complex.
Which is exactly the mission for this deep dive.
Mhm.
We are taking the hood off to decode the hidden mechanics of links, URI schemes, and the actual architecture of deep linking across iOS, Android, and the open web. Because once you understand the underlying routing matrix, like the intent filters, the registries, the fallback logic, you realize how fragile this entire ecosystem actually is.
Okay, let's unpack this. Why does tapping what looks like an identical string of blue text trigger such a wildly unpredictable chain of events across the operating system?
Well, to get to the root of that unpredictability, we have to look at the parser level of your operating system. Because your phone isn't reading one unified language here, it is dealing with two fundamentally different structural systems.
Okay, two systems.
Right. So System A consists of standard URLs, hierarchical resource locators. We were talking about strings that contain a protocol, a colon, and two forward slashes. The colon slash is the critical identifier.
You mean like https.example.com or local paths like file? We are dealing with network locations. Yes, exactly. The presence of those two slashes tells the operating system's parser something very specific. This is a path to a resource. It instructs the OS to, spit up a network stack, perform a DNS resolution, initiate a TCP handshake, and fetch data from a server or a local file system.
So it's basically a fetch quest.
Right. It is entirely location-based. It's a request to retrieve a document and render it in a client, which is usually a web browser.
Got it. But then we have System B, which kind of shifts the paradigm entirely.
Yeah, it really does.
System B consists of action-based URI schemes. And the defining structural trait here is the complete absence of those forward flashes. You have a format that's just scheme.data. So a link formatted as tel plus 414-3222-4567 or mailto.user at example.com.
What's fascinating here is how the parser reacts to the absence of the //. The moment the OS sees a scheme followed immediately by a colon and data, without the slashes, it skips the network stack entirely.
Oh, wow. It just bypasses it.
Completely. It knows it isn't looking for a location on the internet. It interprets this string as an explicit system-level command. The text before the colon dictates the action dialing, drafting, mapping, and the text after the colon is the payload for that action.
I think the best way to conceptualize the difference is to, step away from the code for a second. Imagine a split screen in your mind. On one side, you have System A. It is the difference between handing someone a map pin with an address, which is the URL pointing to a location, and on the other side, System B, handing them a walkie-talkie and shouting, call this phone number. The action URI is a direct operational command. One expects a destination, the other executes an action.
That's a perfect way to visualize it, and the translation of that walkie-talkie command relies entirely on the operating system's internal routing layer. Imagine the OS, whether it's iOS or Android, acting as this central dispatcher or a traffic controller.
Right.
It intercepts the tap event before any application can claim it. It looks at the scheme prefix and checks it against an internal registry of native capabilities.
So let's talk about how Android and iOS actually handle that interception, because they do approach it using different frameworks under the hood. On Android, this is handled by the intent system. When you tap a mailto.link, Android broadcasts an implicit intent. It essentially yells out to the system, hey, I have an email address payload. Who knows how to handle this?
Yeah, and iOS uses launch services to achieve a similar internal handoff. The operating systems come hardwired with core definitions. They universally understand that tel maps to the phone dialer, AMS maps to the messaging client, and geo maps to the default navigation software.
Right, but the complexity arises because the execution of those payloads isn't actually standardized across device manufacturers or like cellular carriers, is it?
No, not at all. It's actually kind of a mess.
Yeah, the sources highlight this specifically with the SEM scheme. You can theoretically append a body payload to an AMS.link to pre-fill a text message. You click the link, and your messaging app opens with a promotional code already typed into the text box.
In theory, yes.
Right, but depending on whether the user is on a Samsung running One UI, a Google Pixel, or an iPhone, the parser might strip that body text entirely. The intent extras, the additional data beyond just the phone number, are interpreted differently depending on the specific software handling the broadcast.
Exactly. And the geo scheme suffers from similar fragmentation. A standard geo coordinate might open Google Maps on an Android device and perfectly drop a pin. Tap that exact same link on an iOS device, and if it attempts to route to Apple Maps without the precise formatting it expects, the coordinate translation might fail entirely, dropping the user's pin in a completely unrelated location.
Which is just wild, and I guess this highlights why the OS has to act as such a strict mediator or traffic controller. The OS doesn't just blindly pass these commands along, it enforces security boundaries.
It has to. If an Action URI bypasses the network stack to trigger native hardware functions, the risk of abuse is enormous. A malicious website could embed a script to silently execute a tell command to a premium rate international number the very second the page loads.
Oh, that would be a nightmare.
Right. To prevent that, the OS implements user permission gates. It suspends the routing process and forces an explicit user confirmation. It generates a system-level dialog box, requiring the user to physically tap call or send before the final trigger is pulled.
Right, so the OS manages the routing table, but it enforces a manual safety catch for destructive or costly actions.
Exactly.
The native schemes are highly regulated by the OS. It knows what a phone call is, it knows what a text message is, but the friction really starts when third-party developers enter the ecosystem. I mean, we don't just use our phones for core telecommunications anymore. We use Spotify, Slack, WhatsApp. Developers wanted the ability to trigger their own apps from the web, which led to the creation of custom app schemes.
Right, and this initiated an era of software routing that was essentially the Wild West. Apple and Google allowed developers to invent their own URI prefixes. So instead of just tell.app, a developer could register Spotify or WhatsApp, or literally any random string.
Wait, so anyone can just invent a scheme? What happens if I click a Spotify.link, but I uninstalled Spotify yesterday to save storage space? Does the traffic controller just crash?
Well, that's exactly the problem. The theory of permissionless innovation is sound. But in practice, custom schemes introduce two catastrophic flaws into the operating system's routing architecture.
Okay, what's the first one?
The first was the complete lack of collision control, which we call scheme hijacking. Because there was no central registry verifying ownership, any app could claim any scheme. You could download a malicious flashlight app, and that app could silently register Bank of America with the OS intent registry.
Oh, wow. So the OS traffic dispatcher wouldn't even know the difference. The next time you tap a link from your bank, the OS intercepts it, sees Bank of America, and just blindly hands your secure payload over to the malware.
Precisely the issue. And the second flaw is what we call the unhandled scheme problem, which goes back to your question about uninstalling Spotify. Custom schemes only function if the destination software is actively installed on the device.
Right, of course.
So if a developer sends a marketing email with a Spotify.link, but the user uninstalled Spotify the previous day, the OS attempts to route the command, finds an empty slot in its registry, and the process simply terminates.
Ah, I see. This is where we need a better analogy to understand the breakdown. It's like walking up to a public payphone on the street, picking up the receiver, and dialing extension 404 because that's the short code you use at your specific office building.
Oh, that's a great way to put it.
The global telecommunications network has absolutely no idea what to do with that input. The routing mapping for 404 only existed inside your building's internal switchboard. Out on the public street, the command is meaningless. You just get a deadline.
And for the user tapping a screen, a deadline manifests as a frustrating error dialog like, Safari cannot open the page because the address is invalid. The user is completely stranded. And from a product design perspective, stranding your user in a digital void is the worst possible outcome.
Which obviously pushed the tech industry to a breaking point. You have a system that is highly vulnerable to security hijacking and guarantees a broken experience if the user doesn't have the software installed. The ecosystem required a modern hybrid solution to bridge the gap between native app capabilities and the fail-safe nature of the open web.
Right. And the industry's answer was to deprecate the reliance on custom URIs and transition to HTTPS-based deep linking. Apple branded their architecture Universal Links, and Google implemented a nearly identical framework called App Links.
So they basically abandoned the decentralized app name format and returned to System A?
Exactly. They started using standard, verifiable web URLs like https://open.spotify.com, followed by a track identifier.
Here's where it gets really interesting, though, because the transition back to HTTPS introduces a massive technical challenge. If the link uses a standard web protocol, the default behavior of the OS should be to send it to the web browser. The OS has to somehow intercept a standard URL, figure out if it corresponds to an installed app, and route it to that app instead of the browser all in a fraction of a second without lagging the user's phone.
Right. And to achieve that zero latency routing, the operating systems shifted the verification process to the installation phase rather than the click phase.
So wait, so it checks when you download the app?
Yes, it utilizes cryptographic verification files hosted on the developer's domain. When you download Spotify from the App Store, the operating system doesn't just install the code. It quietly reaches out to https://spotify.com and looks for a hidden, highly specific file in a directory called .wellknown.
Oh, right. For iOS, this is the Apple App Site Association file, the ASA. And for Android, it looks for the assetlinks.json file.
You got it. These files are served securely over HTTPS. They contain a JSON payload that lists the specific app IDs authorized to intercept links for that domain. The OS downloads this JSON file, verifies the cryptographic certificates, and silently updates its internal routing table right then and there.
That's incredibly smart.
It is. The OS now knows with absolute cryptographic certainty that the app installed on the device is legally associated with the Spotify.com domain.
Which completely neutralizes the scheme hijacking vulnerability we talked about. A malicious flashlight app can't claim https://bankofamerica.com because then cannot alter the JSON file hosted on the bank's secure web servers. The OS will only route the link if the server-side file and the client-side app ID match perfectly.
If we connect this to the bigger picture, the brilliance of the ASA and Asset Links architecture is the fallback mechanism. If you tap the HTTPS link and the app is installed, the OS intercepts it and launches the native experience. But if you tap the link and you do not have the app installed, the OS simply lets the link behave exactly as it was originally formatted. It routes the HTTP request straight to the web browser.
The public road is always open. If the internal Office extension fails, the system automatically dials the public web address. The user is safely routed to the mobile web version of the exact same content. They get to listen to the track or read the article regardless of their local software environment. There are no error screens, no deadlines, and no stranded users.
Exactly. The infrastructure of the open web becomes the ultimate safety net for native application routing. It merges the universal reliability of a web location with the powerful execution of a system command.
Wow. We have mapped an incredible journey through the hidden routing architecture of our devices today. We started with the sheer chaos of tapping a link and not knowing if you're going to open a browser, dial a phone, or just trigger a software error. We've dug through the intent filters, the security gates, the era of custom scheme hijacking, all the way to the cryptographic verification of universal links.
It's a lot to take in.
It is. But if you are listening and want to synthesize this deep dive into a mental model you can actually use, it basically boils down to 3 golden rules.
Right, and the first rule is the structural definition URLs locate. They are destinations. They utilize the forward slashes to instruct the parser to fetch resources over a network protocol.
Rule number 2, URI schemes act. They are explicit commands. They lack the slashes, bypassing the network stack to trigger native system-level behavior.
And the third rule is that the operating system is the ultimate arbiter. It intercepts the broadcasts, reads the intent registries, checks the cryptographic JSON files, and enforces the security permissions before deciding where the data actually flows.
And the overarching technical reality tying all of this together is that nothing in this entire mobile ecosystem is fully universal except HTTPS. Everything else, every custom scheme, every quirky SMS payload is highly system dependent. It relies on a super fragile alignment of your OS version, your manufacturer, and the specific applications occupying your local storage. HTTPS is literally the only common denominator that guarantees a destination.
Which really represents a fascinating shift in how software architecture is prioritizing the web over isolated application silos.
So what does this all mean? We know the invisible traffic controller is making split-second cryptographic decisions to route you to the right place. But exploring this architecture leaves me with a final provocative thought regarding where this is all heading. Yeah, think about it. If HTTPS, the standard web address, is the only true, reliable standard left, and it is increasingly capable of doing the job of dedicated app links, what does that mean for the future of standalone apps? As the mobile browser and web protocols slowly absorb all of this routing power, and as progressive web apps gain access to native hardware APIs, will the entire concept of an app eventually just dissolve back into the open web? I mean, the next time you tap a link and flawlessly transition from a website into an application, ask yourself, how much longer will the underlying code even distinguish between the two?
That is a great question. It really forces us to question if the App Store model is a permanent fixture or just, a transitional phase in software distribution.
Something to ponder the next time you find yourself staring at a piece of blue underlined text.
Thank you for joining us on this deep dive. Keep questioning the systems beneath the glass, and we will catch you next time.